Hello everyone. Let's start today's lesson. Today's topic is predicates and quantifiers. In last class we saw up to satisfiability of a propositional logic problem. Okay, now predicate logic is a little bit more powerful than propositional logic. In the case of propositional logic, we could write a particular natural language statement in the form of a logical statement. And the output of the statement was either true or false. Here also, the output of the statement will be either true or false, but in addition, we will be able to express a reason for the statement and relationship between objects. Now, let us look at an example. Okay, for example, you can see over here the statement P of x is equal to x greater than 3. The propositional logic x greater than 3 has got the subject x and the predicate is greater than 3. Once a value is assigned to x, this particular statement will give the output true or false. Okay, so a statement similar to this, which has got a subject and a predicate, is called a predicate statement. Okay, and it's very similar to propositional statement. In our case, the if then else, this particular example, let P of x denote the statement x greater than 3. What are the truth values of P of 4? So assign the value 4 to x. And is 4 greater than 3? True. So the first case, P of 4 is true. Whereas if you assign the value 2 to x, 2 is not greater than 2. So P of 2 is false, whereas P of 4 is true. Okay. So that is the, when we assign the value to that particular predicate logic, the output we get is either true or false, depending on what is this, the actual value of the x, that is the subject. In this particular case, let A of x denote the statement computer X is under attack by an intruder. Suppose that the computers on campus are only CS2 and Math 1. Only these two computers are currently under attack. Okay, so in that case, what is the truth value for A CS1? We already know that only CS2 and Math 1 are under attack. So CS1 will be false, CS2 will be true, and Math 1 will be true because only CS2 and Math 1 are under attack. So this statement is true only if X is either CS1 or Math 1. For any other value, this particular statement will give the answer false. Similarly, now so far we had seen a single variable predicate. Okay. Now we are going to look at two variables, three variables, all that is possible. Here we have the predicate logic q, x, comma, y. So there are two subjects, x and y. And this denotes a statement x is equal to y plus 3. So what is the truth value if x is equal to 1 and y is equal to 2? If x is equal to 1, then we get 1 is equal to 2 plus 3. Is that true? 1 is not equal to 5. So it is false. Whereas if x is 3 and y is 0, then x is equal to, that is 3 is equal to 0 plus 3. That is equal to 3 itself. So this is true. Okay, another one with three variables. Here are x comma y comma z, where x, y and z are the subjects, and the predicate is whether x plus y is equal to z. Okay, so R1, 2, 3, we have 1 plus 2 is equal to 3, which is true. Whereas R001, it is 0 plus 0 is equal to 1, which is false. Okay, so we can see over here that in general, there can be n variables in a predicate, and it will be denoted by P of x1, x2, etc., xn, as many variables or subjects as there are in the predicate logic. Okay, and a statement of this form is the value of the propositional function P. So whatever is the nth tuple, which has got actual values for x1, x2, etc., xn, that will be substituted into the predicate logic and you will get an n-ary predicate or n-place predicate. Okay. Now, where do we use this in computer program? You have already seen if then else statements. Okay, in the if then else statement, you can see we first have a condition. The condition is always a predicate logic where you can substitute a particular value. In this particular case, the statement is if x is greater than 0, then x is equal to x plus 1. So the subject in this predicate is, predicate logic is x greater than 0, where x is the subject and greater than 0 is the predicate. Okay, so whatever value is just before this if statement for x, that is the value which will come over here for x. So supposing x was equal to 0, then this statement will be false because 0 is not greater than 0. Any other value other than 0, say it is 1, 1 is greater than 0, so this will become true. And then x is equal to x plus 1 will be executed. So since x was already equal to 1, here the value of x will become x is equal to 1 plus 1, which is x is equal to 2 after the execution of this particular statement. Okay, now we are going to look at preconditions and postconditions. Okay, predicates are usually used, predicate logic is used to establish the correctness of a particular program, whether we are getting the required output from a particular set of valid inputs. The valid inputs are called preconditions, and the expected output after the running of the program is called postconditions. Okay, and predicate logic can be used to express both preconditions and postconditions. Now we are going to look at examples. Consider the following program. We are looking at the correctness of this particular program. This is designed to interchange the values of two variables, x and y. And this is the code that has been written. Okay, temp is equal to x is equal to y, and y is equal to temp. What we need to do over here is find predicates that we can use as the precondition and the postcondition to verify the correctness of this program. And then they are asking us to explain how to use these predicates and postconditions to verify that for all valid inputs, the program will work correctly. That means if we have A and B as the input, x will be A and y will be B. And at the end, after this has been conducted, it was to interchange the values. So at the beginning, if x is equal to A and y is equal to B, then at the end, y should be equal to A and x should be equal to B. That is interchanging the values of x and y. Okay, so now let's look at the precondition is the predicate Px comma y, where Px comma y initially could be some value A and B. So x could be some value A and B. And the post condition is finally what the value should be. X should be B and y should be A because we are interchanging the values of x and y. Okay, so if initially x is A and y is B, then at the end of the program, y should be A and x should be B. Then it is correct. So precondition is x is equal to A and y is equal to B. Post condition is x is equal to B and y is equal to A. Now let's look at the correctness. Okay, it's very simple. Just look at each statement in this particular code. If you look at each statement, we already know that the first value of x is A and the first value of y is B. So when I execute this statement, what is actually happening is the value of x is going to be assigned to temp. So here temp will be equal to A and x is also equal to A because it has not been erased. Okay. Then in this statement, we are assigning the value of y to x. So now x will be equal to b. Okay, but y's value has not been replaced, so y is still equal to b. Here we are assigning temp's value to y. And here temp's value is, in the first statement, we had assigned temp's value as the value of x. So temp is now a. So y will become, y is assigned as a. And since we have not replaced the value of temp, temp is also equal to a. So at now the three statements have been run. The aim was to make x equal to b and y equal to a. So what is the last values of x and y? Here, this is the last value of x. So it has become b, and this is the last value of y. This has become a. So effectively, the code, we have shown that the code works correctly, and the values of x and y has been interchanged at the end of the code. So the post condition is now satisfied. Okay, and since we have used general values like a and b, we know that for any valid input, this will be working. So the correctness of the code has also been checked. Okay, now we are going to move on to quantifiers. What is quantifiers? Quantifiers is a particular method by which we are expressing what is the range of a particular predicate. Okay, so if something should be true, how, in which all places in the code is it true? And normally in maths, we see it as for all, there exists, those kind of symbols. And here also, similar symbols are going to be used. All, some, in English statements, the quantifiers are all, some, many, none, few, etc. Okay, we are going to use essentially two quantifiers, two types of quantification. One is called the universal quantification. The universal quantification tells us that the predicate is true for all elements in the universe. Okay, the predicate for all x, p of x. If I say that, it means that for all x values in that particular universe, p of x should be true. The predicate should be true. Okay, so that is the universal quantification. Whereas existential quantification says that if I say there exists x, p of x, what I mean is there exists at least one element, at least one. So there can be one or more, but minimum one element which satisfies the predicate p of x. Okay, and the area in which these predicates and quantifiers are used is called predicate calculus. Okay, now we're going to look at individually. Universal quantifier, the symbol is for all. We have seen this in maths. The universal quantification of p of x is the statement p of x for all values of x in the domain. It's important to note that this p of x will be true only for elements in that particular universe or that particular domain or that particular domain of discourse. If the domain changes or the universe changes, this p of x may not be true. The statement for all p of x may not be true. It is important to specify the universe when we denote a universal quantification. Same goes for there exists also. Okay, so in the case of p of x, if I want to show that this p for all p of x does not hold, I only need to find one example which does not satisfy p of x, because we are claiming that for all x values in the universe, p of x holds. Okay, so if I want to show it's not true, I just need to find one example in the universe where p of x does not hold, and that is called the counter example. Okay, now let's look at an example. Let p of x be the statement x plus 1 is greater than x. what is the truth value of the quantification for all x p of x, where the domain consists of all real numbers? Okay, because the domain is all real numbers, x plus 1 greater than x will always be true for all values. Okay, so here for all x, p of x is always true for real numbers. Okay, now show that p of x is not always true when x is in the domain. Is in the domain to find. How do we do that? I already told you. If I want to show that p of x is not true, I need to find one counter example. Okay, one example where the value will become false. Okay, so this is the example. Let q of x be x is less than 2. Okay, so the predicate p of x is, or q of x is less than true. What is the truth value of the quantification for all x q of x, and the domain is real numbers? One example, we need to find a real number x which is not less than true, 2. Okay, so if I take that the x value is the real number 3, is 3 less than 2? It is not. So this is one example, and by that we have proved that for all x, q of x will not be true. That is x less than 2. In the case of real numbers, it will not be true. Okay, another example. Suppose that p of x is x square is greater than 0. And here the universe of discourse is integers. Okay, find one counter example. So if x is equal to 0, it has to be greater than 0, right? X square should be greater than 0. But if in integers, 0 is an integer. So 0 square, if we take it is 0 itself, it's equal to 0, it's not greater than 0. So x is equal to 0 is a counter example which disproves for all x p of x in the universe of discourse consisting of all integers. Another, what does the statement for all x nx mean if nx is computer x is connected to the campus network? So the statement is computer x is connected to the campus network, and the domain consists of all the computers on the campus. Okay, so the statement for all x nx means that every computer is connected to the campus network. Okay, and for all x nx simply means that for all computers x is connected to the campus network. That means in English, every computer is connected to the campus network. Okay, next, what is the truth value of for all x square is greater than or equal to x if the domain consists of real numbers? Okay, we need to see if we can find one example in real numbers which is going to be x square is not greater than or equal to x. And here we take the value half as the x value. Half square is 1 by 4, which is a smaller number not greater than or equal to x itself. Okay, so we have found one example if it is real numbers. Whereas the same thing, if instead of real numbers, we took a different domain, integers, then this particular statement becomes true because integers are only whole numbers, and that when we square always it will be greater than the number itself. Okay. Now we are moving to existential quantifier. In the case of existential quantifier, I told you there should be at least one value that satisfies the predicate. Okay, for that particular p of x, whatever that condition is. Okay, so when with existential quantification, we form a proposition that is true if and only if p of x is true for at least one value of x. There can be more than one, but there should be at least one. Okay, here also domain of discourse is important. If the domain changes, the meaning also will change. Now we're going to look at examples. Let P of x denote the statement x greater than 3. Okay, what is the truth value of the quantification? There exists an x greater than 3 in real numbers. Okay, there x greater than 3 means any value above 3 is x greater than 3. So there is one value, x is equal to 4 if you take. This existential statement is true. And we don't need to look at more. We only need to show that one value is there which is giving this statement a true value. Okay. Next one, let q of x denote the statement x is equal to x plus 1. Okay, x is equal to x plus 1. What is the truth value of there exists x, q of x, where the domain is real numbers? Okay, because q of x is false for every real number, x cannot be equal to x plus 1 in any of the real numbers. So there isn't a single value of x which we can substitute in x is equal to x plus 1 to make that statement true. So we have to check all values. So this statement is false. Okay. Now, this is similar to the existential statement, but in the existential statement, I told you that you need to have at least one. So one or more values are possible. In the uniqueness quantifier, which is denoted by there exists exclamation mark or there exists subscript 1, that there exists a unique, that is, there is only one value for which the predicate is true. Okay, so this is a special case of existential quantifier. Okay, so normally we don't use this uniqueness quantifier. In its place, we use the existential quantifier itself because existential quantifier and universal quantifiers have got rules of inference for manipulation to show correctness and things like that. So even when uniqueness is to be applied, we will use existential. Okay. Now we are going to look at quantifiers over finite domain. When a domain is of a quantifier, that is real numbers or integers or whatever is your universe of discourse or the domain, if that is finite, all its elements can be listed and quantified statements can be expressed using a propositional logic. Okay, so if the element is finite, there are n elements, then x1, x2, etc., xn. The universal quantification for all x p of x is p of x1 or p of x2 or p of x3, etc., p or p of xn. Okay, sorry, not or, this is and. Okay, the v shape is or. So this is, that is, all these x1s should be true if for all x px should be true. So we can check one by one whether all are true. In the case of existential, it is or. We can check one by one whether at least one value is true. Okay, that is for finite domain. Okay, so example is here. What is the truth value of for all x px where px is the statement x square less than 10 and the domain consists of the positive integers not exceeding 4. So positive integers not exceeding 4 means 1, 2, 3 and 4. So we can check one by one. 1 square is 1, which is less than 10. 2 square is 4, which is less than 10. 3 square is 9, which is less than 10. 4 square is 16, which is not less than 10. So the statement for all x p of x, which comes where the domain is positive integers not exceeding 4, is false because there is one value which exceeds 10. Okay. Similarly, for there exists, what is the truth value of there exists? when the statement is again x square greater than 10, and the universe of discourse consists of positive integers not exceeding 4. Okay, so again 1, 2, 3, 4. And we saw here this is there exists. We need to find one value which is greater than 10. And we saw that 4 gives the value 16, which is greater than 10. So since there is one value, there exists x, p of x is true for this particular domain. Okay, with this, I think I will stop for today and we can continue in the next class.